Hello guys, welcome to the TechoGenius Academy. I am your trainer and today we will unravel a new concept. Please like, share and subscribe to the channel and now sit back and enjoy the video.
Hello guys, welcome to the TechoGenius Academy. So today we are here to discuss the next topic on Linux device driver. Today we will discuss on memory management. What is physical memory, what is virtual memory, how we can access the memory in kernel, how we can access the virtual memory in kernel space, how we can map into that. So there are a few concepts related to the memory management. So before going into this memory management, I just want to give you a brief about like what is hardware communication. It's basically like during the earlier days, the address bus and the data bus was smaller. Address bus used to 16-bit wide and the data bus used to 8-bit wide, right? So further compared to the CPU speed, the peripheral used to work at the slower speed. So as a result, some of the manufacturers decided to have separate address space for the devices and the conventional memory, which is nothing but RAM. For example, x86. It's like a some laptop or computer, that motherboard and all these things. So that is like x86 processor. So this is called like IO ports access. And another decided to have a single address space for both peripheral and the conventional memory. For example, ARM. This is called IO memory access. The x86 family of processors have separate read and write electrical lines for IO ports and the special CPU instruction to access the ports. So in the when we will go to the IO ports, so there will be a special CPU instruction if we want to access the particular port. And the Linux kernel supports both concepts on all the platforms. If the underlying, so whatever that two lines I have mentioned, so that will not support the IO port access. That means then Linux kernel fix it, which are nothing but the use of IO ports in a common ISA peripherals, for example parallel port. And the use of IO memory is common for the PCI devices, for example video card. Okay, so in IO memory approaches is generally preferred because CPU access memory much more efficiently, and the compilers can optimize the code for better register allocation and addressing mode selection when accessing memory. All the devices are controlled by reading and writing hardware registers. Most of the time, a device have a several registers. Communications with the device involves access to more than one register. At the hardware level, there is no conceptual difference between the memory region and the IO region. So we will deep dive into that, like what is memory region, so how we can access the IO region in the kernel space and all. So we'll go into that. So today we will be discussing the kernel memory allocator. So how we can allocate the memory in the kernel, what is port IO and what is memory mapped IO, and how we can request the IO ports and the IO memory in the Linux kernel programming or in Linux device driver programming. So first we will go to the kernel memory allocator. Before going to the kernel memory allocator, I just want to show you some few points related to physical memory and the virtual memory. So it's like 1 GB reserved for the kernel space in the virtual address space. So and contain kernel code and the core data structure identical in all address spaces. And most memory can be direct mapping of the physical memory at the fixed offset. And the complete 3 GB exclusive mapping available for each user space process. So in a kernel space we have to only 1 GB is there, and in a user space application 3 GB exclusive mapping is available. So in that process code and data program stack, memory map files are included into that. So that is not necessarily mapped to the physical memory, and this will differ from one address space to another address space. Only less than 1 GB memory addressable directly through the kernel virtual address space. If more physical memory is present on the platform, part of that memory will not be accessible by the kernel space but can be used by the user space. If your 32-bit platform hosts more than 4 GB, they just cannot be mapped. Each user space process is still limited to the 3 GB memory space. So actually I've just written in a more easy way, like you can understand like how much memory space we have in a virtual address space and all. And so we have 4 GB, and in this 3 GB is the user space memory space. And the memory allocated may not be physically allocated, and the kernel uses demand fault paging to allocate the physical page. And the physical page is allocated when the access to the virtual address generates a page fault or may has just swapped out, and which also include a page fault. So it's nothing but like when you are requesting for a particular page that is in the RAM, so that will come out, and it will execute, and that will be swapped out and all this stuffs. Okay, so kernel memory allocator. So it allocates the physical pages and the kernel allocated memory, and it cannot be swapped out. So if it cannot be swapped out, you have to understand that in that page fault will not occur. So no fault handling required for the kernel memory. So that will only used for user space application. Okay, and most of the kernel memory allocator function also return a kernel virtual address, which is to be used within the kernel space only. So when we will use the kernel memory allocation function, we will get the virtual address, which from where we can access the memory, and we can read and write into these stuffs and all. Okay, so kernel memory low level allocator manages pages. This is the finest granularity. However, the kernel memory management handles smaller memory allocation through its allocator. Okay, appropriate for the medium size allocation. So a page is usually 4K but can be made greater some in some architecture. You can say like 2 pages, 4 at 8 pages and all, and typical the size is 8192 KB. And in a kernel memory allocator, so the second parameter which we need to pass is a flag. So the most common ones are like I have mentioned, it's a GFP kernel, GFP atomic, and GFP DMA. And in most of the coding part and all these things, we are using GFP kernel. And there are few concepts where we need to use the interrupts and all, so there we are using GFP atomic. And the GFP DMA, you already know about this DMA and all. So it's a dynamic memory allocation, so it will allocate the memory in an area of the physical memory usable for the DMA transfers and all. So GFP kernel is a standard kernel memory allocation, and GFP atomic is for like their the RAM allocated from code which is not allowed to block the particular interrupt handlers or some critical sections. And it will never block allowed to and it will allow to access emergency pools but can fail if no memory is readily available. Okay, so the kmalloc is a kernel memory allocator function, which is generally just a memory allocator in the Linux kernel. And for small sizes, it relies on generic slab cache, and which is present, you can see in the cat proc slab info. And for the larger size, it relies on the page allocator. The allocator area is guaranteed to be physical contiguous. Okay, so the allocated area size is about it's like size of the smallest slab cache in which it can fit. Maximum size on x86 and ARM is like per allocation is 4 MB, and the total allocation is 120 MB, 8 MB. So the function is the void pointer kmalloc, and the size we need to mention in the second parameter is a flag which we have discussed earlier. You can free the free allocated area by using a void k-free function, a k-free function, and the argument you need to pass is a pointer. And you can use kz just to allocate a zero initialized buffer. K seek allocate just memory for an array of n elements of size and zero is its context. So that parameters you need to pass as a size, and after that the um, flags and all these things you need to pass. And will be your elements of the array of n elements. Okay, and k relog will change the size of the buffer pointed by the p pointer, and the new size by reallocating a new buffer and copying the data unless the new size fits within the alignment of the existing buffer. Automatically free the allocated buffer when the corresponding device or module is unpropped. So there is some other functions also which is need to have a reference to a structured device. There is a dev kmalloc we need to use in a z kz alloc and kc alloc and k in a k free. So it is just useful to immediate free and allocated buffer, which is nothing but a k free. Okay. So we have discussed a few things in this kernel memory allocator, and now we will go deep dive into the IO ports. So how we can request and access the IO ports. So we'll look into that. Yeah. So port IO. So it'll I have discussed with you earlier in the first slide that it'll use the special class of CPU instruction to perform IO operations, generally found in Intel architecture. Special in and out instruction are used for accessing IO and can read and write up to 4 bytes. IO devices have separate address space from the general memory. This is accomplished by either an extra IO pin on the CPU or an entire bus dedicated for an IO. Since the address space of the IO is isolated from the CPU address space, this approach is called as a isolated IO. Okay, so what we will do now, so we'll just write a simple program just to access the port mapped. So in that we will run the program as a root application using IO system call, and after that we will go to the requesting IO ports. Okay, so there is a some call in a you can say see here request region. Okay, so it will allow to prevent other drivers from using the same IO ports, but it is purely voluntary. And the kernel Linux kernel actually provides interface for accessing IO ports, like allocating and reserving IO ports, manipulating IO ports, string operations, or and you can pause the IO ports also. So what we will do now, we will just go to the terminal. Yep. Just okay, to the root. Yep. So I'll just create a directory, memory management. Yep. So this will be the IO port simple user space application which I am running in as a root. So IO pom.c. Yep. So I'll just include some of the header files. So I just need to define a macro for some port and the IO port section. So we can see this in the when we will use cat proc IO ports. 0xm70. Yep. Starting my function. So we will write that to get the access to the ports. If base port I'll use the IOPOM's CTL IOPOM call system call. Comma 4, comma 1. I'll just display the some error message and exit off on it if it will not happen. So IOPOM is used for setting the port input and output permissions. So in this, the first argument is unsigned long from, and the second one is unsigned long number, and third one is a turn on. IOPOM sets the port access permission bits for calling thread for number bits starting from the port address, which is that first parameter. And if the turn on is non-zero, then permission for the specified bit is enabled, otherwise it is disabled. So the calling thread must be privileged. So this is the thing, and we'll jump into the code. I'll just declare one variable here, char value equals to 0. Great. Val equals to in B base port plus 1. I'm just printing printf seconds x slash n comma my value. So now we can say we don't need the port anymore, means we can use the same call here. And we can mention here 3 0. Yeah. And we can return 0. Yep. So this is the stuff we need to run this. Okay, oh sorry, hyphen o base port, let me clear. Base port. Yeah. So now you are thinking like, what is this ambient? This is for, I can write a comment here, reading a byte from that port. And there is also another call, like another function, which is nothing but a out b, which is used for writing a byte. Seconds 26. Okay, so now we can see this in cat proc IO ports. Oh, oh, sorry. That is not the thing, because this we can't see because we are not requesting the particular region. So that we can do it when we will do the request region. We can just access the particular port because we are not writing here request region. Yes. So we need to request the region of that particular thing. So for that, what we can do here. Okay. So we can probably write a code just to request a region. That will be in the so that in that manner we can request the mm, uh, we can see in that cat proc IO ports. Okay, so IO region dot c, great, hash include linux slash module dot h. So you can see here the request region. So this is the stuff, and after that we can mention that address and that string IO ports and all these things. So start will there is a unsigned long start and the length. So start specify the starting address of the IO ports, length specify the number of ports, and on success the function returns a non-null value, on the error the function returns null. So we can do it here. Linux slash IO ports, yes, hash include, we need to include IO2 here, and the innate one. Sorry. Yep. So we need to define macro here for IO start. Some region maybe we can write it here. So this 40, so this we need to verify in cat proc IO ports. Okay, 6 2, okay. Yeah, it's available. So I'll just initialize some variable here. Start. IU start will be fine because I'm mentioning as IU start in the macro, and the IO extend. Yep. IO end also I need to mention because I needed it later. So now we'll just start our init module function. So unsigned long some test variable I just can initialize. 100 will be fine. Yep. I can just typecast this unsigned long. This looks better. IO end will be your IO start plus IO extend. Print K Kern info requesting the IO region UX percentage So now we are requesting the region. Great. IO start, the first address, the end, IO extend, the last one, and this will be shown in when we will use catproc IO ports. So this is the name of that particular region where we are accessing this particular port. Print K Kern info if it's not there, then the IO region is busy. Great. Okay, this looks good. So now what we can do here, we can just write some data into that. So that will give nice understanding. Con info, writing along data equals to percentage ul test. Yep, this looks fine. And now we will use, so out b is like a writing a byte. So if we want to write a long, so we need to use out l. Okay, first will be your variable which you have initialized, and other will be your IO start where you want to write. Great. So now we have to read also. We'll store into the same variable in Beanie. Sorry, like in L. Yep. In long. Okay. IO start. Yeah. Great. Print K con info, reading along data. And we can return 0 from here. So this looks good to me. And now we can write the exit function. Yep. So here we need to release the region. So as you can see here, we are requesting, and we have to release 2. Print K. Okay, so now we can just copy this. So this looks good. So okay, release region, IO start, IO extend. Yep. We need to include it here, module underscore init, just to initialize the init and exit module. If you're not including, then this will show you the error, because without this you can't enter into this. We can write some. Okay, author will be from TechoGenius Academy. This looks good. Description. It's requesting the IO ports and the license. If you'll not give this, it will taint the kernel. Kernel will be tainted. It will show like this if it's wrong also. So this looks fine to me. So what I can do here, actually I just need a make file, so I can copy the make file from my earlier directories, what we have discussed earlier. Okay, yeah, this looks fine to me. IO region .o. Yep, so now we can do make. Okay. Fatal error. IO ports. Okay, 1 second. Oh, I think so. Port. Yeah, so it's good to go. So now we will just, okay, so I'll just delete some logs from here so you can have a better idea. So I'm inserting the module now. Great. D message. So requesting the IO region 200 to 240, writing a long data, and after that we are reading that particular data. So now we can see cat proc IO ports. Yep, so successfully we can have the access here. We are writing into that particular port and we are reading that. So in this way, so you can request the IO ports. So the function to read and the write words. So there are byte, words, and longs to that IO ports. So we have discussed the in L and the out L, and the strings variants also often more efficient than the corresponding C loop if the processor supports such operations, like then in S and the out S we can use it here. So it's your task, like you can use some strings operations and all these things, so to have a better idea. So now we will go to the memory mapped IO. So the say in memory mapped IO, the same address bus to the say address memory and the IO devices, and access to that IO devices using regular instruction. So here we are not using any special instruction which we have used in IO ports. Memory and the register of the IO devices is mapped to the CPU address spaces. When CPU access an address, it may be referred to the portion of that RAM or the memory of the IO device. So you need to take care of these things. So whenever we are accessing a particular address, it is referring to the RAM or to that memory of the IO devices. And the CPU instruction used for the accessing memory are also used for accessing the devices also, and the portion of the CPU address space will be reserved for the IO devices and will not be available for the RAM. This address space reservation can be temporary or the permanent, and we can see the memory mapped IO in cat proc IO mem. So now how we can map the IO ports in the virtual memory. So it allows for transparent use for the port IO and the memory mapped IO at the same time, as this memory can access in the same way as the memory mapped IO memory. So the mapping is done using the IO port underscore map function. So we have IO port underscore map function, and we can unmap also by using IO port underscore unmap. So we can read and write the data. So if you want to do some 8 byte or some 16 byte, so you can vary, like as it is used for 16 or 32, so you can change the function call. So the these are the following functions. So now what we will do here, we can write this IO port underscore map function to demonstrate how we can use these. First I will just remove this. Okay, make clean, great. So we can just mention IO port dot C. This looks good. Actually most of the things are same, so now what I can do it here, I can just copy IO region to IO port. This looks good. IO port, yep. So we need to request the region. Okay, one sec, I just do the indentation. Yeah, this looks fine to me, at least I can understand. So in this we were using outel in L and all these things, so we can use here IO port map. One sec. Yeah, we have successfully requested the IO region. What we can do here, we can use the IO. We need to declare some pointer here. Static character underscore underscore IO mem mapped. So this same we need to use here. Port map. First will be your IO start, then IO extend, and your name of that port where you can see this name. I think you no need to mention it here, because this is only for IO start and extend, because in a request region we are writing that. In IO port underscore map I can just see this. Okay, so one will be the port and other will be the size of that particular thing. So the last one, we can just mention the prints here. Print K, IO port mapped at reach. Print K. So we have mapped it, and we can now write data. I'm using. And after that we can read the data. and we can print that. So this looks fine to me. We need to unmap also. So this looks fine to me. We need to change it here. Okay. Okay, some error, mapped and declared. Oh, I mentioned 3 times. One sec. Con info con info con info. Okay. We are inserting now. The message. Okay. I have done some mistake here. Just give me some time. Percentage. So we are writing a data 100. Yep. So we can see that. We can see the address also. One second. Yep, this looks fine. So I can just delete the logs to show you the fresh one, the message. Yeah, so we can read the data, and we can write the data, and we can also read the data. And using cat proc IO ports, we can see here also that we can access the particular region. So this is like mapping of IO ports in a virtual memory. So now how we can request the IO memory in a kernel space. So for that we need to use the request mem region. First will be your start, that then after your length, and you can release the memory region by the using release underscore mem underscore region, and you can see this memory mapped IO by using cat proc IO mem, and load store instruction work with the virtual addresses. To access the IO memory, drivers need to have the virtual address that a processor can handle, because the IO memory is not mapped by the default in virtual memory. So to do that, to get the kernel virtual address, there is a special function for that, which is nothing but a IO remap, and we can unmap also by using IO unmap. So these are the function calls where we can use this. Okay, so what's next? In the next session, what we will try to write the parallel port driver, and the PCA and the block driver. So using this memory and all these things. So if possible, like I'll try to cover as much as I can. And please, if you like this video, please don't forget to like, share, and subscribe. And most probably, like I'll upload the more videos soon. Thank you so much.